of mutual repulsion, and that's particularly relevant in this particular aspect because we're looking at electron pairs, which remember are negatively charged. Okay, and we know that they are going to repel from one another. So our learning goals are that students will be able to predict the shape of molecules based on shared electrons and lone pairs, and you'll be able to understand the effect of molecular shape on stability and reactivity. So the electrons are important in determining the shape of molecules as well as how they react as well. So we kind of talked a little bit about Coulombs law a little bit earlier when we were talking about different types of bonding, but also whenever we were talking about earlier this year in terms of electrons and where to fill them up. And Coulombs law basically says that we learned that charges want to repel from each other because they are like charged. Electrons are always negatively charged, and because of that, they want to get as far away from each other as they can. Now, the reason why the electrons just don't keep going further and further and further away is there's actually a nice little positive charge in the middle that's kind of pulling them together. So as a result, these charges are attracted in the sense that they want to stay within a certain distance, but at the same time they want to get as far away from each other as they can. This desire, not really desire, but this repulsion between electrons is what determines a molecule's geometry or its shape. And you can see that with Vesper. And you see this is Vesper theory of puppy orbital hybridization. They all want to get to the food, right? They all want to get to the proton, but at the same time, the electrons are as far away from each other as they can, just based on the fact that that's the way that they work in terms of structure. You can't get them to be any closer together. If you move this one over here, it's going to knock this one, which moves this one, which moves this one. So the valence shell electron pair repulsion theory allows you to predict molecular shapes based solely on the valence structure. And it's based on the fact that electrons repel, and bonds are part of that repulsion, and they will move as far away from each other as they possibly can. Okay, lone pairs push away more than a bonded pair, and we'll talk about why in just a little bit. There are some limitations to the Vesper theory, and the first is that the shapes are not always the same depending on the bond length. So, for example, if you have a CH bond, it has a certain bond length. But if you were to take C and you were to bond it with something like, I don't know, iodine, okay, because iodine is so much larger and has a different electronegativity, it doesn't necessarily produce the same bond length, and it can limit the shape. Another limitation of Vesper is it does not work well for transition metals. Okay, transition metals tend to have d orbitals, which are kind of they're delocalized, so the electrons are kind of here and kind of not. So as a result of that, it doesn't work particularly well for those transition metals. Now, example A1 says, explain why an unbonded electrons have a greater bond between angles than bonded electrons. So what it's saying is, this right here has a greater bond angle than this right here. Okay, why is this greater? And if you think about it in terms of Coulombs law says that you have these electrons that want to get as far away from each other as possible. Well, these electrons that are right here that are represented by these bonds are shared between nitrogen and hydrogen. Yes, it does actually mean that the nitrogen is going to pull these pair a little bit closer than the hydrogen is going to, but it's not a huge amount. And in fact, because they're shared, it's somewhere in between the two. So the pair is probably somewhere in between right here and right here. So because of that, you have this difference in terms of how far the electrons are from this central atom. The lone pair is going to be much, much closer to the central atom than these bonded pairs. The distance makes a big difference, though. Because it's so much closer, what this does is it actually provides a little bit more repulsion for these, and it pushes them a little bit further away from the central atom, making these angles tighter and this one a larger angle. It all has to do with Coulomb's law when we're talking about electron configuration and we're talking about shape.